Hello, Jeters. Welcome back. It is Thursday, June 19th, around 5:11 p.m. Pacific time. And we are going to do part 4, I think, part 4 of keeping on coding, or let's keep coding, something like that. And I think this is going to be a fun one. Well, I think all of them have been fun, but this one, I think we're going to start getting pretty wacky. But before we dive into that, music check. I'm listening to Green Red Productions today, study music. And yes, I am a super nerd that I still listen to study music stuff, even though, well, I guess I'm studying all the time. So, but this one, yeah, it's good. I like these guys quite a bit. I'm trying to get the name here. Productivity, music. It's scrolling on me at the bottom here. Productivity music for studying, I guess. Okay. So that's our music check. As a reminder, we are doing this mostly as a demonstration of mastering the basics. And for our research goals, we implemented our baseline. We implemented our improvement. We're going to tweak this quite a bit today. And I don't know actually how this is going to go. I haven't done any of this, so we'll see. I have some ideas, but we'll see where it goes. And we're going to do a lot of this today. But as a reminder of what it is we're actually looking at, we are looking at TensorFlow, and we were inspired by this fun, deep level of nesting of loops, just to demonstrate that if we could optimize this single control expression, then in theory, we could have a relatively nice performance improvement on each iteration of the 6 levels of nesting here. So this is n to this, hold on, 1, 2, 3, 4, 5, 6, 7. This is n to the 7th. So yeah, that's probably some good optimization potential. And part of our story was basically that we can do an optimization on these. This is not actually the exact one. Sorry. There's so many of these that I might be in the wrong. I was just quickly trying to. Goju's bad. We're going to leave this in. I'm like, wait, where are the -1s and stuff? Let's see here. Okay. I wonder if I can type -1 in here. Because I thought there was a -1. Maybe they fixed it. Maybe people were watching this and... Huh. Maybe, what is this? 529? No, because I think that we didn't start doing this. Where are you? Okay. Well, we know generally like what the shape of this thing is. But I would love to find the actual -1. It makes me wonder if it was inside of the notables. I don't think so, though. Wow, that's an interesting one. Okay. Well, let's actually just go back here. Maybe somehow it did get fixed. Oh, you can still write control expressions. That's cool. You do all this. The team's been busy. Yeah, I thought maybe I sorted it by there. Here we go. Here we are. Okay, wherever I was, whatever that was, maybe that was notables. Now I think we're in the right spot. Okay, my apologies. Yeah, okay, cool. So we basically were making the observation that from this guy here, we could eliminate this -1 and just make this greater than, and then it is potentially faster because it's reduced control expression, conditional operations. All right. So now we're back into Visual Studio. I'm going to make this a little bit bigger here. And I noticed that we are getting a little, there's a couple hundred lines of code in this now. And I don't really like cluttered code. So I created a header file for us. And I'm going to move all our class stuff and essentially our constants over into this guy. And we're going to do matrix test. This is a terrible namespace name. Can we call this something else? Let's call this Goju matrix loops. There we go. Okay, now just change this. See, I have all these hotkey thingamabobs, but I am still don't know how to use this awesome Kinesis keyboard. They moved a couple things on me, so moving the control keys and the escape and tap key, I think, was maybe the thing that's hurting my head the most. I love it though, by the way. If you haven't, oh, that's strange. Oh yeah. If you haven't looked into these Kinesis keyboards, strongly recommended. I think they're fantastic. Okay, so I have this is my namespace. Okay. And now we will include arguments. And this is probably going to complain less about this stuff now. Okay, I should be including chrono here. What else do I need? That might be it for the time being. Let's see. I don't expect this to compile, but it did. Okay. Now, before I continue, I want to quickly talk about this Pragma once thing. While I spent a little bit of time looking this up just to try to understand if this is standard or not, and the consensus was this is not standard. Although a lot of people seem to think that it's not terribly awful. So all right. Wow. Maybe you guys could have started with that. Okay. Important note. Despite its widespread adoption and support by most modern compilers, Pragma once is not part of standard C++. So, given that it's not standard, I don't think we should use it. And I was looking at some of the reasons why on Reddit and other things, like the questions and challenges. Some of it's related to file systems and networking and things that are hard for C++ to kind of know definitively. Like if you have a network path that is essentially identical except for the node itself, and it maps to essentially the same file name, is that Pragma once the same for those two network instances if it's the same file, or is that two separate files? And then other interesting things like that. So you're welcome to use the Pragma once, but I try to not use non-standard language stuff. And part of the reason for that is I've been burned pretty bad in the past doing this and been kind of married to a specific development environment. And I don't love that. So I'm not going to do that. Instead, I'm going to do an if and def of, we'll call this arguments H. And just for additional clarity, we'll do that. And then we'll define this thing. And then we will end if. And this is the end of the if and def. I haven't done this in a while, so okay. It was just complaining about the lack of the matching end if. So this basically functions similarly to the Pragma once. The trick or the difference of this is that this is has a specific name. And so if you have another file with this exact name, then this is going to be defined, and then it won't be able to include that file. So the hope is that we are good enough at generating unique names for the header inclusion rules that we don't block other header files from being included. Now, I want to share that this is quite challenging, especially if you're going to try to do it manually and you're going to include other people's libraries, header files that you don't know. And so some people have tried to come up with specific rules on how to name these things. Some of them say that you should use the relative path from where your project starts to the point of the header file location. I don't know. I mean, I think that can work, but that can still have conflict if you have another exact folder that is following, like from a library, that potentially can have issues. So needless to say, this is one of those very strange things in that it's so simple, yet it's so hard. So I guess maybe I'll just leave it at that. You can use this. That's what I'm going to do for this. And then, yeah, we'll do some other things. Okay. Now, for namespaces, generally what I do is I try to guard everything in the header file inside of the namespace. And I do that because if I do have collisions on other files having a Goju millisecond or other classes that we're going to define here, and we'll probably create at least one more. We're going to create the class, the Goju int, and this Visual Studio, please. This, oh, I know why it's complaining. Oh, okay, here we go. Oh. Yes. Okay. So we want to generally put everything in the header file inside of a namespace to avoid naming collisions. And so that's what we're doing here. And this should break our other code over here. I'm just going to let it, oh, okay, I guess we're good. Probably I turned on the namespace for all the cases. Yeah. Excellent. Okay. Now, one of the things, actually, let's just try to run this and see where we are. I think it was Control Shift F5. Or is it just, yeah, Control Shift F. Oh, no. Just F5. Okay. So this is our optimized version. And then I think what we were showing is we're going to try to load the optimized version first and see if this has any impact on warming the cache, and then show that basically the optimized version is slower because something strange is going on. And then if we inverted this, the optimized version would be second, and then optimized version would be faster. In either case, this is not great. This is like not really showing what we want it to be showing. So let's see if we can fix this. One of the ideas I had, I have several ideas on why I think this is happening, but I want to share that one of the ideas, I'm just going to fiddle with this mic a little bit here. I'm just bumping into the wire as I'm typing. Okay, so one of the things I think could be going on is the compiler can be trying to get super clever on us and doing its fun stuff, which is optimizing our code that's making it not do the thing that we want it to do. So first thing I'm going to do is I'm going to try to yank out these rands. Because I'm just curious if this has any, wow. Okay. So the rands are definitely causing some problems. And that makes sense because while the rand method is just a quasi. Oh, look at this. Maybe. Yeah. So let's increase the loops here. And can add one more here. We want to have two more so we were in the single digit of milliseconds. So I want to put us approximately the 100 millisecond range. So yeah, I added basically 2 zeros, which should give us something closer to that. Like 400 or milliseconds or something. Okay, so this is the optimized version again. And now we have the normal version. Okay, this is promising. This is great. I don't even know if we'll have to do our other thing, but I think we can still do it. So my initial thought was, I had two thoughts on what was causing this. The first thought that I had is calling rand was getting faster every time because the system was getting smart enough to figure out that we were calling rand and then it was caching it in more efficient and effective cached ways. So, because it could see that the rand call is not part of the branching, that the rand was going to be called iteratively for this entire range. It just doesn't know where it's going to exit. So the branch predictors in the hardware can start to get really smart after they've seen this execute and then essentially know that it's not going to exit this loop after so many hundreds or thousands of runs, and therefore it can speculatively execute these rands and essentially pull in more into the cache, knowing that it's seeing this behavior. We're doing essentially the runtime optimization of the hardware for this signature. And this absolutely happens on modern hardware. So if you think that the optimizations are only in the compiler, no. The hardware today has ways to start looking at execution signatures and try to make things faster over and over. For example, you may notice the first time you load up Outlook after your or some large thing, maybe Chrome, the first time you reboot your machine, and then if you close Chrome or Outlook or that big thing and you try to launch it a second time, it could launch faster. Or if you create like a second tab or something like that, these subsequent operations will often be faster. A lot of the reason for this is the modern CPUs have a lot of various optimizations that they can do to make things more efficient. Okay, so now that those rands are gone, and again, the reason why I thought the rands were affecting this is that in my head, it's very clear that this optimized version is simply more efficient than this unoptimized version. And I'll show this to all of us in a moment as we actually implement the subtraction operator, the greater than and equal to operator, and the greater than operator. And it will be just blindingly clear, if that's a thing, people say, that this other one is just more efficient. And my second thought, so my first thought was rand was causing this performance degradation, and it was getting faster because as rand was executing and the CPU was monitoring the optimizations, it was then making the subsequent calls faster because it's caching rand. And once we remove rand, we see that suddenly we're getting way different performance. And in fact, when we're running these, we see now that our optimized system appears to be, or at least in the last two runs, appears to be running faster than the unoptimized version. And it looks like we had two anomalous events this last time. Okay, it looks like it's still faster. I thought those two anomalous events here would have caused it. These are the optimized. And then it gets in the 300s. Yeah, I think that these things are related to me dragging the window. So here's what I'm going to do. I'm going to run this again. And I'm not going to touch the window until it finishes. So we're literally just going to, we're still going to impact the performance because this video is being recorded on this machine. And so is the audio. So it's getting multiple program interference of programs that are co-resident on the processor or the die. And so to run this in a truly scientific way, we would be on a separate machine, and we wouldn't be running things in a co-resident way that would cause us to be impacting the performance. But we're not doing like tier 1 research publication experiments right now. If you were to do that, then yes, you would want a machine that is completely unperturbed by other executing systems, so you can see things in like a truly isolated way, and then run like the proper ablation experiments. Okay, so now it is still interesting because I think we are still suffering a warming of the cache in these first couple of runs, right? Because you drop down, and then I think the warming of that cache persists for the non-optimized version. But because the optimized version is just so much faster, it doesn't matter. Even when this one doesn't get the benefit of the warmed cache for at least these first 4 runs or so, it overall, because we're running like 50 or 20 or whatever, it sort of amortizes that. So it pulls it back down. Think of the thing that we were talking about with the mean and the median, and how, so, right, you can clearly see why we had these two. Is the median is essentially telling us really where the middle point is, which in this case helps us elide away the performance differences that you would have in either cases of long tail distribution, for it being one-offs that or small number of anomalous events that are super lucky to be really fast, as well as long tail that is super unlucky to be really slow. That those are sort of elided away when you use the median. They won't be elided away when you use the mean, and that's why we use both these. And if you're doing like tier 1 scientific research, you generally want to include both of these for this very reason, especially if you know that you potentially could have some anomalous cases or like long tail distributions. Okay, with that in mind, this time we didn't touch the screen, and what we can see is that the total time for the matrix that's not optimized was about 10 seconds. And then the total time for the optimized was about 9 seconds. So now what you see here, which I think is a sort of an important point to drive home, is our optimization, now that we've brought it essentially down to where it's mostly just focusing on this conditional. Again, there's still other things that are happening, right? This conditional is happening and this conditional is happening, but it's happening for both of these things. So the only difference now really is this condition and this condition. And because we're able to run this so many times, which again goes back to the original point of what we were showing, is that this is going to run so many times, which is why we were interested in this, is that we don't generally, or at least I don't generally care about optimizing every control expression. But if I have a control expression that is 6 or 7 loops deep on a hot path that could be executed potentially 1 trillion times, and I can look at it and immediately say, this control expression is not optimized, I can optimize this very easily and show semantic equivalence with very minor changes and make this faster. Why would you not do this? Like, why not? Like, it's a small amount of work to make this change. The only change, again, was changing this -1 and greater than or equal to greater than. That's it. And again, this only works in discrete mathematics. So if you have like a floating point, I mean, in this case, yeah, you generally wouldn't do this type of thing for floating point anyway, but it's generally, I would argue, only safe when you're using discrete mathematics, not continuous numbers. So whole numbers, integers, discrete numbers, not continuous, floating point, real numbers, not that space. But the good news is most programming is using discrete mathematics, and this one was, and so we can use it here, and it works just fine. And so with that simple change, that very minor change, we're able to see a 10% performance improvement. That's crazy. And the truth is, it could actually be more. So let's just go into this and run these. So yeah, it's 25. So if I increase it to, it would be 10 seconds, it would be 100 seconds each. So I don't really want to do that. Maybe what I'll do is I'll increase it. I can increase a couple of different things, right? I can increase the looping, and then I can increase the maximum number of calls. Again, also, another reason why we pull these literals out is that now I have one place where I can think about the looping, and I can change just the looping stuff that I want to change. I don't have to dance around in this file, and I'd have to manually change this, and then I have to go down here and manually change this and this. Or if I wanted to change the actual iterations, I have to go in and change this, and then change this. It's just like, just do it the right way. Just do it the right way, and you end up saving yourself and everyone else basically a small amount of time every time you fiddle with the code. Okay, so this will increase things by about 5x. And 5x, that'll basically put us around 50 seconds. 50 seconds seems pretty reasonable for this to run. So we're going to rebuild everything. So we just rebuilt it. And now we're going to run this again. We're not going to touch the windows. And while that's running, I'll kind of explain the plan that we're going to do next. Even though this could very well show us that this is fast. Wow, look at this. See that first number? Oh, you can't see if the thing's blocking it. Okay. This first number, look at the difference on that warming the cache. That's for 500 milliseconds difference of when the cache isn't warmed versus being warmed. That's quite a bit. So yeah, for those of you that are maybe new to programming and you're looking for easy ways to improve performance of things, warming the cache oftentimes can be helpful. Only in cases when you can warm the cache. Keep in mind, sometimes you can't warm the cache. Sometimes you can. Okay. Right. So after we do this, we're still going to implement our Goju int class. And we're going to do that just so we can count the number of operations that are executed in the slow way versus the optimized way, and then we can output that as well. So in addition to showing the performance changes, the performance deltas, we're also going to look at the operations so we can see that as well. So now what we've done is we've disadvantaged the optimized version as much as possible. And by the way, this is, I think, a really good way to do science, is when you're trying to make an argument on something is better, you generally don't want anyone to question whether or not you're kind of like gaming the system. And so you should do the opposite. You should put your system, or at least this is what I do, put your system in potentially harsher conditions that would force it to be unfairly disadvantaged and show that even in those cases, it still performs better. So for example, by me having this, I mean, what we'd really want to do is just have two separate programs. This one runs, and then it does all of its calculations. Then we run it again with this other version, and then it runs, does all these calculations. Another thing that we can do is we can burn off the caching. And so maybe we'll do that just to get rid of this. But you can see that even with us disadvantaging the optimized, having it run first, and we clearly have an outlier here, right? Like we'll probably see this in the median. Okay, maybe not that much. I guess because it's just one outlier. Still feels like that's a pretty big, yeah. I mean, that's 400, about 400 milliseconds. It's like 20% slower. But anyway, so now there's very little argument that I think anyone could have to say, oh, well, you didn't do this, and you clearly are kind of like short circuiting, or you're skirting these complicated things in the optimized version, and you're not doing that for the unoptimized. So it's an apples to oranges thing. And we're not doing that. You can clearly see this as an apples to apples. If anything, our apples in the optimized version are worse, and it still is faster. And it's faster in all cases. And this is not a margin of error. What I mean by that, this is not noise. So if we ran just one experiment, like just this one, and we ran just this one, then we could be a margin of error. It could be a statistical anomaly. It could be essentially noise. But given that we run 25 of these for each one, and we absorb a non-warm cached on the optimized version, these numbers are, and the difference between these numbers is so large that this is clearly telling us a very obvious thing, that the optimized version is truly optimized. And it's approximately, it's a little less than 20% faster. Let's actually take a look here. So one way to do this is we take this divided by this, and we can see that our system, the baseline system, is 19.5% faster than the unoptimized. So we get almost a 20% performance improvement on this single optimization. That's crazy. And again, this is not rocket science, right? This is us just mastering the basics. Just looking at this saying, gee, I understand laws of transitivity, and I understand discrete mathematics, and that this -1 will be equivalent to it just being greater than, not equal to, because we will strike that. Now, if you have not mastered the basics, you aren't likely to be able to just observe this, which again is why I harp on this so much. Is I think so many people are so eager to get to the kernel stuff or the model stuff, or I want to play around with transformers and diffusion models, and all that stuff is cool. But again, if you think that it's just the hottest topic in technology, and that is the only thing you need to focus on, the likelihood of you being able to fully utilize the benefits of that technology are probably slim, because that technology will have to integrate with other technologies, right? Remember that whole idea that science, there's no single scientific invention that's a panacea. It's a collaborative environment. They're all building off of each other. Okay, so we see that in totality, it's about a 20% performance improvement. Now let's look at the mean. So this is 1723. So this is, we'll say 19% performance improvement. And then we'll look at the last one, which is probably going to be 20%. It's 20, we'll just round up and say, let's say 20.7% performance improvement. Not bad. Not bad. 20% performance improvement by optimizing one control expression. That could be a reasonable number of, I mean, $1,000 AWS bill or $800 AWS or Google Cloud build, Google Cloud bill. And why am I mentioning AWS and Google Cloud? Because this is often what you're doing on these things when you're doing fine tuning, or you're actually training the models themselves. You're in these deep loops for the models with their matrices. That's why, like, this is doing some eigen spatial convolution thing. So eigen stuff is related to linear algebra. Spatial is just a spatial thing. Convolutions are probably related to convolutional matrices, which is like the cornerstone of convolutional neural networks, right? So it's like three separate things, all related to neural networks that are happening here. And again, this is test code. I want to be super clear. This is test code, at least it seems to be. And so it's possible that because this is test code, they just didn't really care. But I care. I mean, on top of that, the tests still have to run. And why not make the test 20% faster by just thinking a little bit harder about this and just doing this in a slightly more optimized way? And yeah, reducing even your own power bill. Cool. We're going to take a short break now, and then we're going to come back and finish doing this class just so we can see the total number of operations. We already are seeing the performance results. So my main speculation was it was related to RAND, but I did have another speculation that it was doing these optimizations on these operators, which it could still be doing. And we'll find that out really quickly, because when we implement the Goju int class, we will prevent it from doing those optimizations. It will have to execute as it's specified here. Once we implement this as a class, it will no longer be possible for the compiler to optimize these like it would normal primitive type. So more on that shortly. Feel free to refill your soda, get your popcorn, all that stuff. And we'll be back in one moment. Okay, we are back. Yes. All right, let's go ahead and implement this Goju int. And this is going to be, let's call this val. And if you construct this with an integer, it's going to do that. Do I need a copy constructor? The default copy constructor, I think, is sufficient because it will use bitwise copy semantics, I think, and that'll just copy the int there. So I think we're good. And then now what we want to do is implement some of these operators. So we'll start with operator is equal to. And this is going to take a Goju int const ref RHF RHS right hand side. This is a const method, and then we'll just say return this val is equal to RHS val. Okay, let's actually implement int const ref val const this val. Yes. Okay. And do we want to set the val? So what I'm doing here is I'm creating essentially my getters and setters, and depending on how I feel this day, I may have them be called get and set, or I may just elide that away. And the reason why is that I like that in C++, I can differentiate that these are two different functions purely by the function signature. So this should compile, I believe. And the reason why is that even though the name matches, this one takes one parameter. This is the setter, is that we need something to set to, but it also returns the value. And I like this a lot because sometimes I set things and then I still want to return things. I don't want it to be like void because I'll daisy chain it. X is equal to Y is equal to Z, right? And so you can set and then stream it out. And then there's other cool things you can do. But then for the getter, it just doesn't take a parameter because it's just going to give you the value. Okay. And then the reason why I did this is I basically wanted to, even within the method itself, I want to invoke the actual getter. So if I wanted to, I could hide these and then essentially keep the access to them just to the class. Or I can force everyone to use these interfaces and I still can hide the implementation because they don't get val directly. So it's like maybe Goju pedantry here, but just sort of what I'm doing. Okay, so we just get our warnings, which is good. But we haven't actually implemented this. Oh, let's actually implement some more. So let's implement our operator. It was greater than, right? Int const as const. Okay. And this is, by the way, oftentimes why I'll say right-hand side is it reminds me that this is the left-hand side. And so as I was trying to figure out the greater than, I was thinking, which way will the operator go? And so it'll be this val, I think, is greater than RHS val. Yeah. Okay. And still const. And I don't do const bool. I guess I could. All right. Sure. I mean, I think that that'll... It might not. Who knows if that'll compile. Okay, so we have these two. And now this one will be, I think, a little bit of the telltale, however you say that word. This will help us, I think, see very clearly why I was saying greater than or equal to is just very clearly slower than just greater than. And the way to do this is you can say this. If this val is greater than, hold on, if this, let's just do it this way. If this is greater than RHS, then return true. If this is equal to RHS, return true. Otherwise, we return false. And I'm not going to add an increment of our total ops on this guy, but I'm going to add a mutable ops member. And this ops guy will be set to 0. And it's going to increment each time we do an operation. And because greater than or equal to is going to invoke both of these, I'm just going to let these base operators increase the total op count. So I'll just do ops here. I could create an interface, but I'm lazy. Yeah. And we're only going to allow the getter. So I think we're mostly safe. And the reason why we're only going to add the getter is that the setter is done completely internally. And the outside world should never be able to set this. It guarantees essentially that as long as we implement it right inside of the class, then there's no funny shenanigans that can happen outside of the class, like whoever's running the experiments trying to like manipulate the results intentionally or unintentionally. The other thing is we make this mutable because we need ops to change inside of these constant methods. And if it's not mutable, it's going to throw errors saying you can't increment ops. You can't mutate ops inside of a non-mutable function. And that's why we say, no, you can. This is a mutable thing. It should be mutable kind of anywhere. Okay. Now, I do not expect that this will compile. Whoops. Okay, it does. But we still haven't added our Goju int to stuff. And we're going to do that now. And the only thing that we need now, I think, is just R and C. And so I'm going to just get rid of all this stuff and just leave C here. Mostly just to see if that's correct. Okay, so that still compiles. And where is that escape key? Is it here? Okay. I'm slowly starting to learn the keyboard. Okay, so we're going to try to compile again. We're going to escape key. Yes. I'm going to get rid of a little bit of the code that was just lying around just to make it easier to read. Okay. Now we're going to change R and C to Goju ints. And this is interesting because this may look like it's doing the assignment operator, but when you invoke the assignment operator at the location where you do the variable declaration, I think the compiler is allowed to optimize this. So it'll just invoke the constructor with the appropriate type. And that will be an int. And so this may compile. Okay. So it's complaining about the minus operator, which is cool because I forgot to implement that. But it didn't complain on that other thing. So now let's implement the subtraction operator. Now I haven't implemented subtraction in a while, but I want to demonstrate something to you, or try to demonstrate something to you, that when you deeply understand how things work and you understand kind of like the semantics of things, in many cases you can often kind of like derive the way things should be just by thinking about it. Just by like, so for 10 years or so, I wrote code in the classified sector. And in that space, you don't have access to, or I didn't have access to the internet, which basically means you just kind of have to know it. There's no access to Stack Overflow. You'd have books and stuff. So I certainly had books, but one of the things that I then leaned on is just my ability to just recall things. And I'm big on using tools to help us, but I'm also big on the idea of not becoming beholden to tools. So like you can still function without the tools. Maybe an example of this is I'm pretty busy these days, but I still like to try to do a small amount of weightlifting as my shoulder's recovering. But I don't have much time to go to the gym or get all the proper gym stuff. And so I'll just wear like work stuff, work clothes. I won't have the right shoes, the right shirt, all that stuff, but I can still do it because I don't need all those things to do exercise. And so similarly, I think that if you can get yourself to the point to where you can just write code and you can just design systems and you can do it on a notepad, on a napkin, in a text editor, I think you are kind of like freeing yourself from being bound to only one environment where you can think. And I think that that's generally pretty healthy, right? It's like the idea that you can drive many different cars, not just the one car that you own. So along those lines, I don't recall the subtraction operator, what the signature is, but if I think about it, subtraction, I can just write this out, is basically just going to be x minus y. And so x in this case will be us, this, and then I'll do minus, and then this will be the right-hand side. And so what do I think? I think that this is going to return a Goju int that is going to be a temporary that's constructed as the result. And that makes sense to me because it has to return something of the same type of this. And whether that's const or not, I don't know that I care. I'm trying to think, does that need to be? We'll make it const, and it'll complain at us if it doesn't like that. Okay, so I have this, then I have my Goju int. This is const for sure, mostly because it shouldn't be mutating inside of this. And then this should be a const method because x shouldn't mutate. So x shouldn't mutate, y should mutate. It should figure out what the difference is and then return just that difference. And it would do this by saying Goju int temp, we'll say, is equal to 0. And then we could say int val is equal to this val minus RHS val. That'll give us the int difference. And then we need to set temps val to val, like this. And then we need to return temp. Oh, and also we want to do this. Yeah. Okay. What does our compiler say? Binary this does not define this operator or a conversion. Oh, didn't I just do this? Hold on. Okay, what is it complaining about now? This val. Oh, right. Oh, and this should just return. I'm consistent in my mistakes. Okay, let's try this again. What do we get? Is this the button? Is this the button? I know I have this mapped to something. There we go. Okay. Is this the one that takes me back? I have these shortcut keys that I don't think I properly shortcutted, which is what I'm trying to figure out. Okay. We have just these two warnings. I want to look at this again and try to understand. And a lot of what I'm doing now is I'm just looking at this because I just want to have a sanity check that I am kind of doing all the stuff that I think I need to do. Okay, so we have operator subtraction, and then this increments the ops. This creates this temp guy. And by the way, we can So I wanted to write this out in long form, but we don't have to do long form. We can do short form, which is this. And yeah, that should hopefully work. That work. Okay. That worked. So we're just embedding this inside of this and just it's eliding away the construction of a temporary. Not a big deal, but this code I think is so simple that it's like not that hard. If this were, I mean, yeah, the other version might have been a little simpler, but I don't think it's that bad. Who's to say? My metric is if it looked like this, I'd be like, okay, that's fine. Okay, and then is equal to operator, it checks to see if they're equal to. The greater than, it checks to see if they're greater than. The greater than or equal to, it checks to see if it's greater than, and then checks to see if they're equal to, and then if neither of those are true, then it returns false. Okay, I kind of think that this is looking kind of good, but I fully expected more compiler errors because I feel like there's something I haven't done. Okay, so I've got this, and then, right, so I implemented this, and this allows me to do this greater than or equal, but this is an integer. Oh, but it's going to do the up conversion. It's going to do the up promotion of this to a Goju type, a Goju int, because I added that conversion operator for int. If I remove this conversion operator, then things are going to go to hell in a handbasket real fast. Just so you can see, like, yeah, it's just, so this is being invoked in a bunch of places, but the one that I wanted you to see is not that one. Yeah, this one. No, not that one. Oh, okay. Well, anyway, clearly we need this. And that conversion operator, I think, will do the 7 conversion. And so we've got this subtraction. And then I think that this will convert this to a Goju int. And then it'll perform the subtraction. And then you'll get a Goju int. And then from there, you'll do the same thing with 7, and then 7 will perform these operations. Or Goju int will encapsulate the number 7, and then it can be compared. All right, let's now, because we're adding a lot more weight to this, before we run it, let's remove one of these loops, because I anticipate this is going to take longer. And now let's go ahead and run this. Okay. Don't know why exactly it wants to put it in the background, but hey, what's going on? Oh, it's still running, I guess. Oh, did I do 50 of those? Yeah, I think that's what I did. Wow. Oh, this is going to take too long. Holy moly. What the heck? Okay, I wasn't expecting it to be that slow. That is... Okay. I think it's because it's calling those 2 operators on their own. Let's reduce this. Let's make this only 10 calls. We reduced it another order of magnitude. And now let's go launch this again. Okay, so the Opti's done. Wow, so now the Opti version is 2 orders of magnitude faster than the non-optimized version. And I think it's because the greater than or equal to operator. Oh, no, it's probably that. It's probably that subtraction operation. I mean, it's both, but what we can do is we can cheat here. So let's cheat to make the other unoptimized system faster. And the cheat to make it faster is we won't have it call these guys. We will have it call, essentially do the same thing as those other operators and do it directly inline. And so we'll say this val is greater than this val, or this val is equal to RHS val. And we can make it even faster if we access val directly without going through this val method. But I suspect this is going to be inlined, so it hopefully shouldn't have performance implications with it, I think. So we still aren't dealing with the negative case, but let's see if this improves the performance. My hope is that it does. Okay, that it's still super slow. Okay, so now let's try to be super clever. Yes, we have to return. I don't think we can't return a reference here. We have to return this copy, unfortunately. Okay, but we could let's try to make this screaming fast. And the way to do this is we're going to return this Goju int construction right as the final operation of this method. And we're going to ensure that it gets the right value, because we're going to do this minus HS. And again, I'm calling these directly because I'm trying to make this as fast as possible now, because it's way too slow. And I don't want to see 100x performance degradation. So what this should do is, now if it does perfect forwarding, we can add a potential perfect forwarder here. I think you'd add it here like this. But let's try this first and let's see what happens if this potentially makes this faster. Okay, it is faster. It's significantly faster. So this is helping, and hopefully it kind of makes sense why this is helping. We're getting pretty advanced now, and I'm kind of doing a whole bunch of things at once. So if this is getting a little overwhelming, you're welcome to play this back multiple times to kind of intuit the many steps that I'm making. Now I think perfect forwarding does this. And I don't think this is going to compile. That does come. Wait, what does this say? Okay. Yeah, I know I'm doing that. But it's a perfect forward. It's been a while since I've done the perfect forwarding. So what it's complaining about is you're trying to return. Okay, don't do this in real life. This is bad. This is not good. Don't do what I'm doing. But again, I'm just trying to make this as fast as possible. So the unoptimized version will be closer. I didn't want it to be this slow, right? This is like way too dramatic. So what I'm doing now is I'm hacking it to essentially give me a referenceable object that I can do perfect forwarding on, that's going to stay in existence, that it can use as a reference. So it will make this warning go away. And now we have a global Goju int inside of this that is going to exist each time we call this operator. And then what we're going to do is we will set val equal to this thing. And then we will just return gint. And it shouldn't complain about this now because, well, are you going to complain? Okay. An rval reference cannot be bound to an L value. Okay. Okay. So I think what they're saying, so that's interesting though, because an rval reference cannot be bound to an L value. So are you saying that, again, this is a hack. You shouldn't, you should not do what I'm doing. Because this is so bad, especially if this is multi-threaded and other people are calling this simultaneously. Like, things are going to go wrong so quickly. But again, I'm just trying to hack on this so I can make the unoptimized version faster. So just roll with me here. Let's see if this makes it faster than it was before. Okay, we're still making it faster, right? So we're getting at the heart of this. We've improved its performance by 2x, because it was like over 2 seconds before. And yeah, now it's approximately 1.1 seconds, which is great, but this is still just insanely slow. And so what I want to do, if zero this, is the compiler smart enough? No. I'm going to look back at this code. Just for kicks and giggles, we're going to change this code to be identical to the other code, just to make sure that I'm not doing something else in here that's bad that I somehow have missed. Oh yeah, something. What is going on? Yo, Visual Studio. Hello. Okay. All right. So something still is. What is up here? Outer iterations. Inner iterations. I'm an idiot. Okay, cool. This is. I forgot to change the other Goju int. I'm going to leave this in. I forgot to change this one to the Goju ints. Awesome. Okay. Now we're comparing apples to apples. That whole this whole other one was just applying this for just the slow version. Okay, now I can go back and not do this hackiness because this is like really bad. And I can put this back. Actually, let's just control Z ourselves back to a good state. Yeah. Okay. Excellent. Okay, do a full rebuild. And now let's run again. All right, here we go. So this is now using both of them with Goju ints. And this is very much what I was expecting to see, is that I'd see approximately like a 2x performance difference because of the optimizations. And so this is, I think, more reality. And again, keep in mind that this one's still absorbing the non-warm cache. We can burn this off, but let's just leave it. So what we see, let's just make this a little bit longer, is that now we are forcing the compiler to not optimize these. You're not allowed to do your fancy optimizations because I think it was still doing optimizations on those greater than or equal to and -1, and it's not allowed to do that now. Now it has to call the operators that I have because it doesn't know that it's a native type and it follows the native type properties. So this is something that you should be aware of, is in many of the programming languages, when you have native types, they can be optimized to the compiler's delight as long as it doesn't violate the specification of the language. But oftentimes with user-defined types, they can't be optimized like this because they don't know if the semantics are intended to behave a certain way. So even though we have our class that just contains an int inside of it, it doesn't know that that's all that's going on. And so it has to play fair. And when it plays fair, then now we're seeing some notable performance differences. The last thing that I want to output is I want to show the operation differences between the non-optimized and the optimized. So you can also see concretely why this unoptimized version would be running so much slower. And that, by the way, this function is getting way too ugly for me. Like if we do a part 5, I'm going to come in and hack on this just to clean this up. I might do a part 5 too, just because there's a couple other things I kind of want to look at. But now I want, sorry, I have this habit of whistling when I start going into deep thought. I want to I want the R and the C ops for each of these. And I think I can just get it here. R ops is equal to R dot ops. I can call that, right? That's no, but I can now. Okay. Cool. Okay. And now I'm trying to think if this number is going to roll. Maybe, maybe not. But let's just call this unopti R unopti C. We have to set these to 0. This is going to be the total. And do the opti version. And then for this, we're going to int R ops equals 0. C ops equals 0. R ops, C ops, and total. This is the optimized version. Yeah. Total opti R equals the R ops. Total opti C is the C ops. Sorry, this will be plus equals. Yeah. And now this guy will have a similar thing, but this is the unopti. And we need these guys. I know I'm doing a little copy pasting. Sorry, I'm being lazy. This is R ops, C ops. Try to compile this. It compiles. Is that the escape key? And now this is my level of pedantry. Okay. This is going to be the matrix unopti ops. And this will be the matrix opti ops. Come on, dude. Okay, yeah, my brain's not working anymore. There we go. Something like this. Now, this is going to be the one unopti first. This would be total unopti R plus total unopti C. Part of the reason why my brain's hurting here is it's inverted. And so the opt's being called first, and then, sorry, the opt's called first, then unopty, but I'm swapping the output order. And so it's causing my brain to seize up in my massive OCD because it shouldn't be inverted like that. Just so you understand why I'm stalling out here. Okay, let's look at this. Let's try to build this. So now we're trying to do the total unopty. We have that here. These guys get reset each time. This is the total opty. Okay, let's just run it and see what we get. I have a sneaking suspicion this isn't going to be exactly right. Why would that be the case? I feel like it's the lifetime right for those Goju ints. It's not entirely clear. Oh, was it this slow before? Interesting. These should not be the same numbers. So that's a bug. Let's figure that out. And then these performance differences, I think that they're kind of what we were expecting. Okay, let's take a look at this. Total, opti, these guys get reset, R ops. Like, why is this not turning blue? It's strange stuff. Total unopti, total unopti, total opti, total opti. Those are plus equals. Okay. Let's see. Yeah, like I don't like that these show up. Like, why is this showing up as blue and this is showing up as white? It probably means nothing. Yeah, it's just Visual Studio's highlighter doesn't highlight properly. Okay. Now, why would these be the same? Max iterations opti. Okay, let's go over to this thing again. Oh, okay. Yes, I understand. I thought I changed it back, but I didn't. Guess maybe I didn't get that far. And then this should not have this here. Okay, so in theory, what this will do, this is where things are going to get quite interesting. In theory, this will... Oh, right, I was doing it the slower way. Okay, let me just explain. One may think that now we're going to have twice as many ops. By the way, what is this negative? This one still should have been invoked. Oh, it was. Okay, I see. There's crazy side effects that were going on. So basically, this guy was having a plus plus ops here. So it was just saying this is one operation. And then it was doing the subtraction operator as a second operation. Whereas, no, it doesn't even make sense. Yeah, it's quite strange. They still shouldn't be the same. Anyway, so what this will do now... Oh. No. Okay. What this should do now is this will call into the greater than operator. And then if this is true, it's going to short circuit out. It won't call into the equal operator. This is super important. So let's just make this explicit, and let's say bool, let's call this greater than is equal to this. This is slower on purpose. We'll make this faster after we do this one iteration. Equal to is equal to this. This is going to force both of these to be called. And then we're going to say return greater than or equal to. So if either of these are true, it'll be true. This should ensure that both of these get invoked, which then will increment the plus operator on both of them. It's not clear to me why this isn't happening, but maybe it's a conversion operator that's happening under the hood. But let's run this code and let's see what we get. I've noticed too that our counter has been reset to 0. Now it's good that they're both the same, but it tells me something is wrong with our math. And I guess if anything, this is going to give us a strong segue into part 5 to figure out what we've broken, or more specifically, what I've broken. So it shouldn't be showing us these same numbers. What is this number? 500 million. Which it's really interesting. Yeah, and we're going to have to clean up this code because this is just too not pretty. All right. So these are our Goju ints in both places. And I wonder if it's doing that conversion operator, if it's doing it potentially in an opposite way of what I'm thinking. Yeah, so this should... Okay, let's just take a look at this for a second. Oh, right. Okay. No, so maybe this is doing the right thing because, I mean, in some sense, that we change this to... Oh, no. I take it back. I was thinking that we had changed this to that from this, but I was actually describing, I think, the or behavior inside of the greater than or equal to. So if we have the r is greater than 7, let's just try to do something here. What we should see, function 10, I think. Okay. So this one, RHS is 7. And this is, yeah, so val, that's right. So what I'm doing in my head here is I'm looking at the val here, which is 0, which it should be. And then RHS, which is 7. Is val greater than 7? It is not. And so this will fail, and it did increment the ops. So now I'm going to hit F11. I'm going to hit F5. And we go back again, and we see now ops is set to 1. It's 2. It's incrementing. And that's all good. And RHS is staying 7 each time. Okay, so I'm going to exit out of our debugger here. Let's see. Turn that off. Okay, so now I want it to see this, that it's going into this operator, the greater than or equal to operator. Okay, now this, the ops is equal to, yeah, cool. Ops is equal to 0. So let's F10 this. It should be, huh? Oh, I think that's F11. My bad. 10. One of the other things they did on this keyboard that, just as an aside, why I'm also struggling, I have to remap a bunch of things. So they have a function key, but the function key doesn't map to the numeric digits. So it's not function key 1, which would be F1. Everything is shifted 1 number to the left. So the function key in 1 is actually F2. And so I was trying to have it go F10, which is step next. And so I hit 0, and that actually invokes F11, which is step into. And anyway, just to give you some sense of my struggles, I'm going to get there. Okay, so I want F10, which is function and the 9 key. Okay, so greater than is false. Great. And the ops... Did the ops increase? Yeah, the ops increased. Okay, and then we step 1 more, and then ops increased again. So that's great. That's what we wanted. Okay. And so we did that. And then I want you to run some more. And now F10. This must be our C, I think. Okay. And then we will run again. F10. Okay. Okay. Interesting. Okay, so we'll step 1 more time here. F10. And now this is the 3rd iteration. Mm-hmm. Oh. I think I sort of ish know what's going on. Sort of. It still doesn't make sense to me. Okay, maybe we'll end here. So this will be another cliffhanger. I think I know why this is going bad now. I'm still a little confused on why it's giving the same value, but I get why the ops are not correct, I think. Yeah, see, you've got the R has the 4 ops, and then hold on to that in your head. And now we're going to step through to the next call. Go back here. R is... Oh, I see. Okay. Oh, okay. This is actually pretty straightforward-ish. Is because this is false, anything ANDed with false will be false. So C will never be invoked. But the part that I'm confused about... Oh, no, I'm not confused. Yes, I know. I know exactly now, I think, why. Do I? I'm getting close. Getting close on why this is going wrong. But I don't want to spoil it. So I'm going to end now and leave this all with you. But let me show one more time what the actual output is, so you can see it and then ponder it between now and part 5. And I think for the most part, these results appear to be correct. I was expecting it to be about a 2x performance difference. We're seeing about a 3x performance difference. Kind of makes sense. We can optimize this a little bit more, which we'll do, which will bring it back down. But now we can clearly see that the optimized one is performing significantly faster, which is really the core thing we wanted to show. And we've got 10 iterations. We can see things are being called the right way. We can see the counter is the same, all of this stuff. We can see the mean is notably improved. Same with the median time. And this is our big question mark. Like, why are these numbers the same? They shouldn't be the same. I have an intuition on at least one reason why they are the same. And it's a bug that I can fix in the next version. But that still doesn't... Yeah, there's still one more missing piece that doesn't accommodate for... Oh, maybe it does. Okay, yeah. Okay, maybe I've got it on why this is happening. Shoot, maybe I don't. I thought the implementation was slightly different, and now that I looked at it, I'm a little... Okay, we'll continue this in part 5. Now you get to see, I think, what it like really looks like when I'm in the trenches and I'm trying to figure this out. I don't want to spoil the first piece on why this is going wrong. One part I'm fairly certain I know why, and it will be probably very obvious once we look at it. But there's still a second piece that's happening that it's not clear to me. And we'll have to figure that out on the fly together. So anyway, I hope this was super interesting for you guys. I feel like we have achieved our initial goal, which is we've done the experiments and we can actually check this off now, because we are getting essentially the performance differences, and more so than I think I initially thought. And that's mind-boggling. Like, that's... and it looks like it's pretty correct. We'll have to do some more experiments to just validate like the true cases, because we should see performance differences even when counter is increasing now. But the initial goal of trying to show that this optimization would improve things, I think we can very clearly see now, is that the new version it's on the order of close to 4x faster than the original unoptimized version. And I think that's super fantastic because it goes to show that this is still just the basics, but we're able to take code that is super advanced machine learning stuff, doing all these fancy eigenspatial convolutional things, and just go back to very basic arithmetic, very basic Boolean comparisons, understand that there's a subtle optimization here that we can make, and we've just 3x'd the performance for the system. We've 3x improved it. Cool. I feel like that's pretty good Thursday. So thanks, everybody. Until next time.